我们介绍这个静磁的部分呢，介绍到现在，如果做个整理的话 ，you're going to see that the electromagnetics the formulas 这个在电磁学里头这些公式呢，非常的对称 ，OK， 非常对称。所以我先介绍一下什么叫 dual equation。dual equation 的意思呢是说，if you have two sets of equations, the two sets of equations can be transformed from one to the other if you do a systematic substitution of variables. 你如果很有系统的，如果有两组的这个公式 ，and then you can do systematic substitution of symbols to transform one set of equation into the other sets. And this kind of equations are called dual equations. 很好玩，在这个静磁学跟静电学里头呢 ，for electrostatics, you can create, you have a set of variables: electric field intensity, electric flux density, permittivity, polarization vector, charge density, voltage, dot product, cross product. And on the other hand, you have another set of variables and operators for magnetostatics. B is magnetic flux density, H is magnetic field intensity, and mu is permeability, M is the magnetization vector, current, and vector potential, cross product, dot product. So if you do a systematic substitution of symbols in one system, you can transform the equation into the equations in the other system. For example, 这是对应的变数 ，OK? So for example, if you pick up the equation from magnetostatics, curl of E equal to 0, and then you keep this operator, but change the curl operator into gradient, into divergence operator, and at the same time replace this E, electric field intensity, with this symbol B, then you immediately create one of the two postulates for the magnetostatics. So this tells you that if you remember equations in this system, you can create equations in this system, okay? And this is just because of symmetry of the physics between magnetostatics and electrostatics. 很好玩，非常的对称 okay? Well, you can, I can give you a second example. For this divergence of D equal to rho, this is Gauss law, right? For this Gauss law, you can convert this Gauss law into Ampere's law by changing this divergence to curl, and then you have a symbol D. The other counterpart symbol for magnetostatics is H, so you replace this D with H, so you have curl of H, and then this law is replaced by the J, the current density vector, so you have Ampere's law. 很好玩 right? Now, the two sets of equations are called dual equations. We have third example here. Once you have a formula for the electrostatics, the electric flux density is defined through this expression. So you change D, you look up this table and you change D to H. You change epsilon to 1 over mu, and then change E to B. Then you create another equation, another formula in the magnetostatics. 所以这是很有趣的这种对称的现象。这个世界其实很对称，很好玩。那但是呢，你要小心 ，not all the equations are dual equations. For example, for this E equal to minus gradient of V, 这是 define 出来的。你可以看到这个负号呢是来自我们定义就无限远的地方，它的 electric potential has to be equal to 0. If you do a systematic substitution of E and V with the variables in this table, then you don't get you don't get this equation because of this minus sign. Okay, and this is gradient. All right, you change this gradient to curl. 所以这个式子呢是定义出来的，并不是最原始的这个电磁学的式子是这个是定义出来的。所以 these two equations do not follow the dual equation manipulation. 所以要小心一下，这个当你碰到 electric potential 跟 vector potential 的时候 ，OK， so this is just a sort of another way for you to remember some formulas. If you know this formulas in the electrostatics, then you can create equations in magnetostatics with this exception. Okay, any question? Okay, 所以这是 dual equation 的式子的概念。Well, just like the boundary conditions for electrostatics, there are also boundary conditions for magnetostatics. 你会发现我们介绍花很多时间在介绍静电学。那静电静磁学它有它的对称性在那个地方，所以 once you learn about electrostatics, you can sort of borrow a lot of concept from electrostatics and apply the concept to magnetostatics. Okay, so the same thing. We have boundary conditions for magnetostatics, and up to this point, this is very standard and also the familiar operation for you. If you have something divergence of B, divergence something equal to 0, then you can create the boundary condition for the normal component of the vector, right? Divergence of D 等于0，告诉你说，你可以算出它的这个垂直方向的D 场的连续性。同样的 ，if I have divergence of B, then you create a small pillbox at the boundary and allow the thickness of this pillbox to be 0. So you only have to take care of the surface here and on the top and on the bottom. 那中间这一环的面积呢，你可以不理它，因为你要求的是边界值，所以呢，这个面积非常非常小。Given this, you only have to take into account the surface on the top and on the bottom, and then so immediately you have the boundary condition for the normal component of the magnetic field. 所以呢，很快的，右边是0， so you get a result that normal component of B field is continuous across the boundary. Okay, so this is straightforward and simple. So once you learn about electrostatics, it's much easier to learn about magnetostatics. You can always remind yourself how you get the boundary conditions for electrostatics, right? 所以这很快的一个结果。另外一个结果呢 ，the second postulate of magnetostatics is the Ampere's law. So you bring out the Ampere's law, that is curl of H equal to Ga. So with curl operator and also the Stokes theorem, then you can create this cross loop integration. And on the right hand side is the current. When you do this operation, don't ever forget the right hand rule. 你的右手定则要晓得这个电流是有方向的，这个 H 是有方向的。那这个方向性呢是 follow your right hand rule. Okay. Now with the curl operator, you can really do this kind of cross loop integration for small loop across the boundary. Okay. 在这里呢，你有一个 small loop across the boundary, and then because you are calculating the boundary conditions, so the path here and here are going to be negligible. 因为你在求它边界值，所以呢，这个路径的积分你要算出来，这个路径的积分你要算出来，但是这个呢，这个厚度是无限的薄，所以这两段呢的积分你不需要做。Okay. So finally you get the tangential component of the magnetic field intensity, and on the right hand side, because if you have a surface current, 你如果有一个表面电流的话呢，右边这里不可能等于0。OK， 所以呢，你如果有个表面电流在这个界面上，譬如说金属的话呢，then you end up having a discontinuity for the H field, the magnetic field intensity. OK， 那所以呢，这个它的 tangential component of H field is continuous if there's a surface current. OK， 这个 surface current 的话呢，它流这个方向，所以呢，它是等于是它的这个你如果把这个 surface current 做一个积分，朝着这方向积分的话，你就得到一个电流，这是surface current density. Okay, and you know that the H field has a direction, and this is defined as the tangential component of the magnetic field because you integrate the field tangent to the surface. But on the right hand side, you have a current. There must be a relationship associated with the directions for those three quantities. And if you just use the right hand rule, you can figure out that the take a reference direction for AN2, okay, and then you have this kind of general expression for the tangential component of the H field. Okay, this comes from the right hand rule. And I want you to compare this with the normal component of the D field. If you ever remember, this is the boundary condition. 这是这个 D field 的边界条件。你可以看到它对称性在那个地方。And then for this expression, you also take into account the reference direction for AN2. AN2, this is 1 and 2. AN2 is going outward from material 2. 永远记得这个面的方向是在这个面的朝外的方向。Okay. If you take a reference direction as AN1, then you have this direction. And this reference direction is quite important because it tells you which one, D1 or D2, is before this minus sign. Okay? And so this calculation is going to give you a sign of rho s, the charge density, 因为电荷有正有负。同样的这个电流呢 you have to pick up the reference direction for N2 to write down H1 before H2. Okay, and then you can get the proper direction of the surface current. Okay, and basically it tells you that the tangential component of a magnetic field intensity is discontinuous for a surface current density at the boundary. If there's no surface current at the boundary, then you don't have this term, and the tangential component of the H field will be continuous. OK， 所以在这里呢，如果说这不是一个导体的话，那你会有这个 normal component B field 是连续的 ，tangential component of H field 是连续的。但是呢，如果是导体的话，导体 by definition there's a lot of charges, so you can create current on the surface. Okay, so you have discontinuity. 所以这是边界条件。Any question? So this is sort of concept that you can borrow from the electrostatics. So I go through this a little bit fast. 有没有问题？没有问题 ，right？ 都很简单。好，那同样的，在这个when we talk about electrostatics, we have such an example with the electric field going to a boundary with the angle. Or the same thing, we can have a magnetic field going to the boundary of two materials with an angle of alpha 1. And we want to figure out the direction of H2 in this material. 那在之前我们做的例子呢，这里是 electric field， 这里是 electric field。哇，所以这个题目对你来说已经很简单了 ，right? Basically, if you want to figure out the direction of this H2, you need to figure out the normal component of this H field and tangential component of this field. And then you have sufficient information to know the direction of this H field, right? 有问题？很直接 ，right? 那我们上回已经介绍过，就是 normal component of the magnetic flux density is continuous, and tangential component of the H field is continuous. Well, 在这里呢 let's specify that these two materials are non-conducting material. OK， 所以呢，我们就把这边界条件拿出来一个用。所以第一个边界条件，你没有这个表面电流 ，so the tangential component of H field is continuous。那不管它表面有没有电流 ，normal component of B field is continuous。So this will offer you the information about the tangential component of the H field in the second medium and normal component of the H field in the second medium. Okay, because B can be converted into H by dividing it with the permeability. Okay, 所以呢，很快的，let's pick up this. Let's figure out the tangential component of H1. Basically, this tangential component right here is equal to this H field multiplied with sine theta alpha because this angle is equal to this angle. 所以这个太简单了，讲的你都快睡着了，其实已经睡着的了。So easy. Well, let's get the easy start, and then we're going to go into a little bit more complicated calculation. Okay, so this is so easy because H1T is equal to H2T. The H1T is very straightforward, this component. So you take a sine theta alpha, multiply this with H1 to get this tangential component. Once you have the tangential component for H2 inside this material, then you need to figure out the tangential component of H2n. And H2n is equal to B2n divided by mu 2. So let's first figure out B1n. And B1n, from the normal component, basically B1n is the normal component of H1n multiplied with mu 1. 所以呢，这个垂直方向量的话，基本上这个切线方向是 sin alpha 1， 垂直方向就是 cosine alpha 1乘上 h1。Okay, and then you multiply it with mu 1 to get B1n. But according to this boundary condition, B1n equal to B2n. So you do a division, B2n divided by mu 2 to get you the H2n. Wow, this is so simple. Immediately you have the tangential component of H2 and the normal component of H2. So with the normal component and also the tangential component, then you can construct the H2, right? And this angle tangent alpha 2 basically is equal to H2n H2t. That's it. So easy. 所以这个很容易就算出来了。所以 you get everything. 然后这个 H2t 的 magnitude 就是这个的这个平方加上这个平方开根号。OK。所以这是边界条件。边界条件呢，在解微分方程的时候很重要。基本上电磁学是由微分方程来描述的，所以呢，边界条件会不断的被使用到。OK， 在解电磁学的问题的时候。Any question? Well, if no question, then we look into another analogy between electrostatics and magnetostatics. 在这个 electrostatics, we have electric circuit, right? We have electric circuit. Now, before I do anything, let's just think about you have electric circuit governed by V and I for an electric circuit. And this comes from actually electric field. Okay, this comes from electric field. And for magnetic field, you have B and H. And this is proportional to current. How do you create electric current inside an electric circuit? Well, the way you create electric current comes from that you apply an electric field to your system, your circuit. So this is a consequence And this is your source. Right? 在这个磁学里头呢，你怎么产生？你是产生 B 场，来自你的电流。So this current is your source. This B field is your consequence. 所以呢 ，at this moment，你已经开始感受到，在这个静磁学跟静电学的这个两个系统里头呢，它对应的变数，在静磁学里头，电流对应的变数其实是对应到这里的电压，这个磁场呢对应到的变数是你的电流，这个是在static electrostatic case, and this is magnetostatic case. Okay. 所以你要进一步的想说 ，in electrostatic, you have Kirchhoff's current law and Kirchhoff's voltage law. Perhaps you can write down the same thing for magnetostatics. 了解吗？我在介绍里头这个数学之前，先给你一个物理的观念，可以了解得来。来，在静磁学的电路里头呢，你的电流是由电场来造成的，所以电场呢，这个电压是来自你的 source。那结果呢是产生电流。在静磁学里头呢，你是用电流产生你的 magnetic field， 所以呢，你的 source 呢是你的电流，但是呢，你产生的结果是 magnetic flux。Okay, this is magnetic flux density. So the same thing, the same concept as magnetic flux, because this is basically is the surface integration of B. 所以呢，在静电学里头的电流对应到这里的 phi， 在静电学里头的电压对应到这里的电流。OK， 那有时候呢，你有 n 个电流在那个地方，所以我们来看一下这个例子。OK， suppose that you have a toroid like this, and then you have magnetic flux going as a loop inside this toroid, and you apply a current into this coil to generate this magnetic field, magnetic flux inside. Okay, and now you want to calculate the relationship between this current and the magnetic flux inside. So first you apply Ampere's law. Okay, this is the Ampere's law. And if this gap is really small, well, in fact, it's not necessary to be very small, but basically there's a gap distance of Lg. Then the magnetic field crossing this surface is going to be considered as a normal component of the magnetic field, right? 所以你的 Ampere's law 你可以把它写成两段，一段呢是在这个 gap 的地方，然后呢Hg, suppose that you have a field of Hg in this region, and then multiply with the gap length, and for the rest you have LF and HF. OK， 那这个东西呢，可以是你要有很强的这个磁场的话，你可以用铁锌，这个铁锌这个物质呢叫做 ferrite， 这个东西是一个很强的磁性物质。OK， for the purpose to increase the magnetic flux density. Okay, so you have this equation. 这个 G 代表这个 gap， 这个 F 代表 ferrite 的这个地方。那这时候呢，you don't know yet what Hg and HF are. You need to find the relationship. 因为这个式子有两个变数 Hg, HF. You need to find another equation to solve these two variables. Fortunately, you can apply the boundary condition, the normal component of B field in this gap, and inside this material are continuous. OK， 所以呢，这个 HF、Hg 的关系，你可以把它找出来。So you have two equations in this green box, in these two green boxes. With two equations, you can calculate the H field, and then with the H field, you can convert it to B field. OK， 你可以得到这么一个式子，这是代数的运算。然后呢，在这里，你如果把这个面积乘上去的话呢 ，if you multiply this B field with the surface area, then you can convert this B into the magnetic flux across this area. 所以呢，你可以整理成这个样子。整理成这个样子的话。You feel that this equation is so similar to the electric circuit. Look at this. 在我们的这个讨论里头，这个电流对应到电路的电压。OK， 所以呢，我们把这个 Ni just rewrite this into Vm。底下，你在电路里头，你有 R equal to conductivity, area, and length. 但是呢，你在这里一比，这长度、面积，这底下 conductivity 改成了permeability. OK， 所以呢，在这里。在这个 magnetic circuit 里头呢，你有一个新的东西，叫做 magnetic reluctance, Ls mu. OK， 这个东西叫做 magnetic reluctance, and then you can write everything into this simple compact expression. And this phi, I just told you, this phi is an analogy to the current in an electric circuit. So voltage divided by R give you the current. 所以你发现这个式子呢，其实是跟电路的式子很像 ，right？ 在电路的式子里头，电压除以电阻得到电流。那我们说在 magnetic circuit 里头，这个电路的电压相对应到的就是 magnetic circuit 里头电流，电路里头对应到的电流呢，就是对应到电路里头对应的电流就是对应到 magnetic circuit 里头的 magnetic flux， 在这里有没有 magnetic flux 对应到电路的电流？电路的这个电压呢，对应到 magnetic circuit 的电流。Okay, I hope that you are not confused when you look at those equations or formulas. I want you to start from this point. Okay, I is consequence of V. B is a consequence of I in magnetic circuit. 所以你在找你对应的这个 counterpart symbol 的时候呢，应该从这里上头看了。你在讲义上头可以注明一下，这个 B is a consequence of Ga。OK， 在 magnetic circuit 里头，然后在这里看的话，就比较不会整个乱掉。So this is a magnetic circuit. 所以这个 toroid 这个 magnetic circuit 基本上包含两个部分，一个是你可以把它写成，可以把它写成这么一个电阻，然后呢，这么一个电路 ，OK， and then you have RF and RG and VM. Basically, you have this. Okay, and rotating inside this circuit has some sort of magnetic current that is your phi. 这个 I 是告诉你说这里头的对应的这个电流就是你的 phi. Okay, so you have phi equal to Vm Rf plus Rg. Okay, right here. So you can convert this magnetic circuit into an electric circuit and then use the familiar Ohm's law to do calculation. And this Vn is equal to Ni. And this R is equal to what? L mu S. 有没有问题? So you can use the your familiar Ohm's law circuit theory to calculate the magnetic flux. 可以哈，好。我们来看一下，我把它做个整理。这里头呢，基本上是来自这个静电学跟定磁学之间对称性。Okay, you have curl of H equal to Ga, and for electric circuit, you have curl of E equal to F. F is the electromotive force. Okay, 所以呢，这个 Vm 在这里是来自电源，我们把它叫做 magnetomotive force. 在这个地方叫做 MMF, magnetomotive force. For this VEM is called the electric motive force. And the counterpart symbols of the electric current in magnetic circuit is the magnetic flux. And the electric resistance expressed like this is replaced by the magnetic reluctance expressed like this. Okay. 所以呢，你也可以 You can also write down the Kirchhoff's voltage law for a magnetostatic loop. 在这个电路里头，你把所有的EMF 都加起来，会等于你在这个电路里头的 voltage drop. Right? So let's do the same thing. Do the summation of all the MMF in the magnetic circuit. That is equal to the summation of all the Ni in your circuit. On the right hand side, you have magnetic reluctance multiplied with the magnetic flux, because this is the counterpart symbols for the I in the magnetic circuit is phi. 所以呢，你把这个 I 换成 phi，R 呢，在这里呢重新定义，在 magnetic circuit 里头是 magnetic reluctance. OK。看这个 symbol， 然后呢互换一下这些这个变数，这个也是其实也有这个 dual equation 的味道在里头。OK， 好，有了这个工具之后，你还可以这个写下 Kirchhoff's current law for a magnetostatic node。对于这个 Kirchhoff's current law 来讲的话 ，you have summation of total current going into a node equal to 0 at a steady state, because a circuit node does not accumulate charges. The same thing, you have divergence B at any circuit node of a magnetic circuit. So you can do a summation of all the flux, magnetic flux at one node and get nothing. So this means that the whatever magnetic flux go into a node has to come out. OK， 所以这个电流的部分呢 ，Kirchhoff's current law for current is modified into this equation for magnetostatic circuit. 所以你有1对1的这种对称性的话，那你解问题的时候 ，if you solve a problem for magnetic circuit, then you can just borrow all the concept from the electric circuit. OK， 可以吗？没问题 ，right？ 好，我们来看一下这个 magnetic circuit。当你看到这个 magnetic circuit 的时候，第一个步骤呢，就是把它变成 electric circuit 的样子，因为你已经熟悉了 electric circuit。OK， so you have one MMF here, you have your second MMF here. So just put the your source here and here. And then you have the magnetic flux going around in this circuit. And the magnetic flux basically is the same concept as the current in the electric circuit. 所以呢，你先把这一段这一段的这个 magnetic reluctance 把它 define 出来，把它切成3段。第一段 the first section, second section, third section, all right? And each section has the magnetic flux, magnetic reluctance R1, R2, R3 在这个地方。OK， 那 R 呢，就等于 L divided by the permeability multiplied with the cross-sectional area。OK， 所以这1对1的置换的东西。So you can create this circuit。然后呢，在这 circuit 里头，这里相当于是这个电路里头电压源，这里是电阻，然后呢，这里是这个 phi 1 phi 2相当于电流，所以你都会解了，有没有？我们来用这个 Kirchhoff's current law, for example, all right. For example, for the magnetic flux, when it's drawing like this, then the magnetic flux going to this branch is phi 1. OK， 那在这个地方呢，就是 phi 1加上 phi 2。从进入这个 node 的 magnetic flux 就是这个加上这个， so you have phi 1 plus phi 2, and then you have phi 2 in this loop. So you only have phi 1 going to this branch. So let me draw the nodes, P1 nodes, right? For P1, if you have phi 1 right here, and you have phi 2 right here, then you have phi 1 plus phi 2 here. Right, 这是 Kirchhoff's current law give you this this relationship at P1. So this is very consistent with the Kirchhoff's current law. 所以呢，在这个 branch 里头，你有在这个 branch 里头，你有 phi 1 plus phi 2 multiplied with R1 as a voltage drop, and then in this loop, the phi 1 going through this R3, so you have a second term right here, phi 1 R3, and the whole thing is equal to the MMF of the circuit loop right here. So you have N1 I1. Okay. So this is basically just the electric circuit model. And for the second loop, you can apply the Kirchhoff's voltage law again to write down the second equation. For this second loop, you have 2 MMF. 这个外头这整个 loop, you have 2 MMF. Okay. This is the voltage rise, and then this is voltage drop. 从正到负，所以你这里有个负号，就像你放了2个这个电压源在这个地方一样。如果它的方向都放的一样的话 ，you have minus sign. So basically, you are doing this. VMMF I summing over all the VMMF, and on the right hand side you have RI and then phi I. OK， 所以呢，在这个 loop 里头呢，一样经过 R1 的 you have phi 1 plus phi 2， 经过 R2 的 you get phi 2。So with this, you have two variables phi 1 and phi 2. So you can calculate phi 1 and phi 2 to get the answer. All right, phi 1 and phi 2. 所以你可以找出来，譬如说这里经过的这个 flux 有多大，然后呢这里经过的 flux 有多大，然后这里经过的呢有多大。So basically you get the answer, right? 刚刚这个式子就是用电路的方法来算。那跟这个一样，你看到一个 magnetic circuit 的时候 ，you first convert it into electric circuit, okay? And the same thing, you get this magnetic circuit and convert this into electric circuit. 那在这里头呢，你注意到这个 magnetic flux is always confined inside this material. So this must be some magnetic material. OK， 你如果有这个铁丝性物质在这里头的话，这个 magnetic flux 都被 confined 在里头，外头的话很少。So this is how you make an efficient magnetic circuit. You use magnetic materials to confine your magnetic flux. OK， 问题？没有问题？所以从一开始上课，我们再回来看一下，一开始上课 I introduced the concept of dual equations, right? 一刚开始上课的时候，我介绍这个 dual equations， 所以今天一开始上课我就告诉你说，这很多静电学的问题可以借过来用到这个静磁学里头来。所以呢，告訴你說 the boundary conditions for magnetostatics, in fact, is also dual equations for the electrostatics. And then continue from this, the discussion of the dual equations. Then I tell you the magnetostatic magnetic circuit. 所以呢，你又借了这个静电学里头的这个 electric circuit 观念呢，来解这个 electric circuit。OK， 这里又是一个 dual equation 的两个系统在那个地方。OK， 好，我们现在要进到另外一个概念，这个概念呢也跟静电学里头的 capacitance 很像。OK， 我们来看一下，静电学里头呢 ，a capacitor is a device to store charge。还记得在静电学里头有电容这种东西，那a capacitor is a device to store charge to store electrostatic energy。那在静磁学里头呢，有相对应的这个元件，这个元件叫做 inductance or inductor， that has inductance。Okay, and inductance is a device. An inductor is a device to store magnetic flux. OK， 所以我们来看一下它的这个静电静磁学的对称性。For electrostatics, you have capacitance equal to charge stored in a device per voltage, right? So you have charge stored to some, say, parallel plate capacitor or cylindrical capacitor and so on. So you have positive Q minus Q right here. And this device can store charge at the same time store electrostatic energy. Well, same thing if you have a current loop. And the source for magnetostatics is a current, so you put a current source here. So in this loop, you store magnetic flux. So you can sort of figure out that there's some sort of physical quantity that is proportional to the magnetic flux divided by some currents. That is equivalent to a capacitance in electrostatic case. 那但是呢，这里头如果一环或者是两环或三环不太一样，这个物理特性会不太一样，所以呢，你会把它放到比如说放一个这个 n 环在里头。OK， 那这个东西我们把它定义成一个物理量，叫做 inductance。 So this is so the magnetic flux stored inside a coil per unit current. We call this inductance. OK， 所以呢，我们来看一下这个 inductance， 你可以看到这个写出来的量基本上就是这么一个式子，N multiplied with magnetic flux divided by current. This is called inductance. But very often that you have several coils nearby, the magnetic flux could go from one coil into another coil. 这个 magnetic flux 不像电流那么容易控制在一个区域里头，那这个 magnetic flux 会到处跑 ，OK， 那所以呢，你必须小心的设定就是这个 magnetic flux 是从哪里来的。所以呢 ，if the magnetic flux is associated with the self coil, the same coil, the magnetic flux generated from this coil penetrate the coil itself, then we call this 511. Okay, 511 means that this magnetic flux comes from the current 1 entering the coil 1. 也就是说，这里头的 indexing 你要很小心的去了解一下这个 phi mn this refers to the current. 第一个电流或第二个电流或第三个电流。This N refers to the coil. Okay, so if I have a current in the first coil, then this magnetic flux inside this coil due to I1 is called 511. Okay. And if I have a second coil, this is I2, C2, and this will generate magnetic flux going to this first coil. And this phi is called phi21 because the first index refers to the current. It comes from the second current. And the second index refers to the loop. It goes into the first loop. The second current goes into the first loop. And it's called phi21. 哇，头昏了，对不对？没有头昏的举手，没有人举手，就是每个人都头昏了。我有一个这个简单的这个记法，这个简单的记法是什么呢？这个电流的 symbol 不是 I 吗 ？coil 不是 C 吗？这个mn 我就把它叫做 IC。OK，IC 是什么？大家都晓得 ，right？ 所以呢，第一个 index refers to current， 的第二个 index refers to coil。So this just help you to remember the indices, the meaning of the indices. OK， 所以你只要记住这个 mn 其实就是 IC，I 就是电流 ，C 就是 loop， coil number of coil， then you can remember this。和教补习班一样，一定要告诉你怎么记东西。我们休息10分钟再回来。